Functions are the fundamental building blocks of calculus. They describe precise relationships where every input has exactly one output. Imagine a vending machine. When you press button A1, you always get the same snack. This predictable relationship is what makes functions so powerful in mathematics and science. Here we see a vending machine representation of a function. Each button represents an input, and the snack that comes out is the output. Notice how pressing button A1 always gives chips, and B1 always gives soda. This consistency is what defines a function. Mathematically, we write this as f from x to y, where x is the set of inputs and y is the set of possible outputs. The notation x maps to f of x shows how each input is transformed into its corresponding output. The most common visualization of a function is its graph. Here we see the quadratic function f of x equals x squared. For every x value on the horizontal axis, there's exactly one y value on the vertical axis determined by the function. Limits are all about understanding how functions behave as we approach specific points, even when the function might not be defined at those exact points. They form the foundation of calculus, allowing us to define derivatives and integrals. Imagine walking toward a door. As you get closer, your distance to the door decreases. Even if you never actually reach the door, we can say you are approaching it. In mathematical terms, your position has a limit at the door's location. We start with the function f of x equals x squared minus 1 divided by x minus 1. What happens when we substitute x equals 1? Direct substitution gives 0 divided by 0, an indeterminate form, but this suggests we should simplify the expression. Notice that x squared minus 1 factors into x minus 1 times x plus 1. Cancelling x minus 1 from numerator and denominator, we get that f of x simplifies to x plus 1 for all x not equal to 1. Let's look at the graph. The function behaves exactly like the line y equals x plus 1, but with a hole at x equals 1. The hole is located at the point 1, 2. The value the function approaches as x gets closer to 1. From the left, as x approaches 1, the function approaches 2. From the right, as x approaches 1, again the function approaches 2. Therefore, the limit exists and equals 2. Let's understand the concept of continuity in functions. Continuity means the function's graph can be drawn smoothly, without any sudden jumps, breaks, or holes. Here is a graph of a continuous function. Notice how the green curve is smooth everywhere. You could trace it without lifting your pencil at any point. This is the essence of continuity. No sudden jumps, no missing points. Now, observe this red curve. It looks similar at first, but at x equals 2, there is a sudden jump. The graph breaks into two separate pieces. This means the function is discontinuous at that point, because we would need to lift our pencil to continue drawing. There are several types of discontinuities. First, a jump discontinuity occurs when the left and right limits exist but are different. Next, a removable discontinuity is like a hole in the graph. The limit exists but doesn't match the function value. Finally, an infinite discontinuity occurs when the function grows without bound near a point. Formally, a function is continuous at a point A if three conditions hold. F of A is defined. The limit as x approaches A exists, and the limit equals the function value at A. Limits aren't just abstract mathematical concepts, they have powerful real-world applications in physics, engineering, economics, and computer science. Let's explore some key applications. The derivative, fundamental to calculus, is defined as a limit. Here we see secant lines approaching the tangent line as h approaches 0. The slope of the tangent line is the limit of the slopes of these secant lines. Integrals are also defined using limits. The area under a curve is approximated by Riemann sums, and the exact area is the limit as the rectangle widths approach 0. Here we see how using more rectangles gives a better approximation of the true area. In engineering, limits appear in tolerance specifications. A part might need to be manufactured to within 0.01 mm of the design specification. This is essentially a limit concept, as our manufacturing precision approaches the tolerance limit. The part becomes acceptable. In finance, continuous compound interest uses limits. As the number of compounding periods per year approaches infinity, we arrive at the formula A equals P times A to the RT. Let's explore functions, limits, and their crucial applications in machine learning. Consider this sigmoid function commonly used in machine learning for classification. The sigmoid function approaches 0 as x goes to negative infinity and 1 as x goes to positive infinity. This bounded behavior makes it perfect for probability outputs. The solution comes from analyzing the exponential term. When x is large negative, the denominator becomes enormous, driving the function to 0. When x is large positive, the denominator approaches 1. Now let's examine a fundamental limit in machine learning, the derivative used in gradient descent. For the function x squared, we can visualize how the difference quotient approaches the derivative as h approaches 0. The algebraic solution shows the limit exists and equals 2x. This derivative is exactly what gradient descent uses to optimize machine learning models. These concepts become crucial when optimizing machine learning loss functions. Consider a loss function we want to minimize. Using derivatives, which are limits, gradient descent iteratively moves toward the minimum. Continuity ensures that small changes to model parameters lead to predictable, small changes in the output. This stability is essential for reliable training. In summary, functions and limits form the mathematical foundation for machine learning. Understanding these concepts helps design better models and training algorithms. I hope you found this video helpful. If you enjoyed it, please give it a thumbs up. Subscribe to the channel, leave a comment, and share it with your friends. Your support means a lot. See you in the next video.